Hello class, and welcome to the Chapter 4 lecture. So today we're talking about procedural abstraction. It sounds fancy, it's not that difficult, just a little software engineering buzz term there. And functions that will actually return the value. Up until now we've seen a whole lot of procedural stuff where we just execute some statements. So now we'll look at functions where we will actually get a value back. That value can be any valid data type. Just going to overview what we're going to be talking about, and we'll start here. We'll dive in with top-down design. So really what this means, top-down design is we take what we want to accomplish, we break it into tasks that are kind of coherent. And what we mean by coherent means that the task logically makes sense. Everything we do within this this task or this subtask fits together. So we do this iteratively until our tasks are very small and very cohesive. So we don't want big monolithic 500-line functions to do a whole lot of stuff, right? We want to have smaller units that are more coherent, that will do a lot of related stuff instead of having a whole bunch of stuff done by one function. So, called stepwise refinement, because we will break these into subtasks iteratively until, our smallest subtasks are very coherent and they're relatively easy to code. So this makes the program a whole lot more legible. And as we can see, we have some benefits here. It's more legible, easy to understand. We can perform maintenance on it easier. We can develop it easier, of course. And we can test and find bugs easier because when we perform unit testing, our units are small, right? Simple input, simple output. So that's really all top-down design is, starting with a big program, breaking it down into pieces. All right, predefined functions. The standard template library is your friend. This is the predefined functions C++ comes with. So here's an example, the square root function. You see basically a function is the function name, and then within the parentheses, we supply the function arguments, the function parameters, depending on what you want to call it. So that's how we call a function here. Now here's the beauty of the standard template library. Now, I can just make this one call. If I come in here, I'll have to include my math header. If I want to calculate the square root of 16.2, that's all I have to do. There we go. So otherwise, what I have to do is define the square root function. Square root functions, depending on how much you know about numerical analysis, the square root function will require a logarithmic base 2 function. That's also something that if I didn't have this CMath header, I would have to code by myself. And I've done this kind of to prove a point here. We also need a ceiling function, which is relatively easy to implement. But you see, the logarithmic function in particular requires a whole heck of a lot of math. And I can get this to 4/10,000ths precision. I can't get this more precise than that. I could maybe study up a whole lot, consult, but the point is these are experts that have coded these library functions for us. We know they work, we know they work well, we know they're pretty much bug-free. There's no such thing as bug-free, but they're relatively bug-free. So that's the advantage here. I don't have to reinvent the wheel, and I know I got good functions, right? So instead of coding my own square root, my own naive square root implementation, I use this one, okay? My answer deviates a little bit from this if I code it by myself. Depending on what precision you need, it may not do, okay? And again, we may have bugs on boundary cases, corner cases. I haven't tested my implementation thoroughly. So yes, this takes a double or an int and returns the double. So in this case, 9 would return 3. We saw 16 returns 4.02492, and we can extend that precision out further with the flags. So yeah, this is a function call. As we see, function name and then argument list in the parentheses. Now, when this returns a value, you can use this within any other expression. So, if we want to set the value of bonus equal to the square root of sales divided by 10, what we'll do is just go ahead and code it like this. The compiler will substitute the value returned by square root sales into this expression and then divide it by 10. Likewise here, if we want to display the value, the compiler will first substitute the return value of square root area and put it in the output stream, standard output stream. So here's your syntax. As we saw, function name, and then your argument or method, or your parameter list within the parentheses. Now, if you have more than one argument, functions can take 0 or more arguments. If you have more than one, they're separated by commas. Okay. So here's one example, square root area, and then a multi-argument example, power, the power function. So we'll raise 2.5, this is our base, to the 3.0, okay? And just to show you, power, 2 to the third, we know that's 8. There we go, voila, 8.0. And to show you that it does return a double, we'll change this a little bit. Make it return 8 point something. There we go, 8.5741. That's how we call a function. Function, argument. Libraries. As I said, the standard template library is very much your friend. Now, the libraries you have to include these manually. We don't include all libraries in a program because then the executable would be huge. We would be including a whole bunch of function definitions in the binary, the executable. So include, the include directive includes a directory, includes the library rather. So in this case, we saw we had to include CMath to use square root as well as PAL. So pound includes CMath. Up until now we've been including IO streams so that we can do basic IO, see out, we can display output, read in input. Okay. Using namespace standard is also necessary for any of the the newer non-old C style libraries. We have some other functions. Here's an example, absolute value. This also requires the math header. Now here it tells us return value is of type int. No, it's overloaded. If you give it a double, it will return a double. If I'm not mistaken, this should return 5.5, yes. And to show you that this is indeed the absolute value function, go ahead and run it with a negative value and it returns the same, 5.5. Now you see in the latter half here, they talk about the floating point absolute value. Doesn't matter. Absolute returns. If you use the math absolute, it's overloaded and will accept and return a double value as well, a floating value. Random number generation. This becomes really useful when we want to prove things. We want to perform tests or simulations. Now, it's important to note that this is a pseudo random number generator. It is not a true random number generator because we don't have a true entropy source, like say from the environment, which some true random number generators utilize. In this case, we use the system clock. So that's why we have to use the time library here when we use our pseudo random number generator in C++. Now, to generate a random number, we have to first kind of declare, if you want to think of it this way, a random object. This is our seed value for this srand object. our seed value is the system block. That's what time 0 means, or time null. You know, we can also say time null. It doesn't matter. Now, to generate a random number, we say rand. There we go, 27,173 is what I get. So we can get any number between I believe it's rand min we'll have to include our limits header, and then we can actually view the limits from the headers from the from the library. Rand min. Okay, well, you know what? Rand min is 0 by default. Sorry about that. We need rand min. I was thinking short min, and I'll tell you why in a sec. All right, so this means that we will produce when we produce a random number, we produce any value between 0 and 32,767. That's what that means. Could be any number between there. Now, keep in mind, again, this is deterministic in that if we know exactly the millisecond at which we perform these actions, we can't calculate the value. So it's pseudo-random. However, it will. From an end user perspective, you're usually not going to capture. You're not usually going to be able to do this in a deterministic fashion. So you can think of it as any random number between 0 and 32,767. Now, the reason I was thinking of rand min, random is just an alias for short, the rand max for short max. And so you can see rand max equals short max, which is kind of an alias there. So that's a short value. And by the way, these don't come out of nowhere. It's not wizardry. So if we look in here, we actually have access to the library. It's open source. We have complete and utter access to it right here. Don't change stuff, of course. Oh, it's been some mistake. Let's see. There we go. Yeah. Aha. So here we have our limits. Scroll down. There it is. There we go. So we have our definitions, some of our definitions here, and they can refer to other places. But you see, we have complete and utter access to our library here. So if you want to tinker and you want to look around, this is definitely a good place to look at how C++ works kind of under the hood. So yeah, the rand function will generate a random int anywhere between 0 and rand max, which we saw, here in my system 32767, 2 to the 15th minus 1. Now we can scale our random numbers. If we want, let's say 32767 is way too high. We want a random number between 1 and 100. Okay, if we say percent 100, if we do the modulus sign and then 100, this will give us any number between 0 and 100 minus 1. So this should give us anywhere between 0 and 99. Let's go ahead and run this. 74. All right. So, notice I said I wanted 1 to 100 and not 0 to 99 effectively. Well, and I can go ahead and offset this by 1. Easy enough, right? And then I can be guaranteed to get a number between 1 and 100. Okay, in this case, it threw 73 at me. So when we do percent, that will give us a number between 0 and 1 less than the argument that I give it. So, if I want 1 to 100, I can offset this by 1. That way 0 plus 1 is 1, and 99 plus 1 is 100. Okay? And they give you the example of a dice. They say, hey, instead of, between 0 and 5, we want to offset it by 1 and say 1 to 6. And that way you can kind of simulate rolling a 6-sided die randomly or pseudo-randomly here. Simulate rolling 2 of them, you do it twice. Generate a random number x where 10 is less than x is less than 21. Well, you could do between 0 and 12 and just add an offset of 10, right? 12 minus 1 is 11, and if you add 10 to both, you get a number anywhere between 10 and 21. That's random number generation. Casting. Okay, so we can change data types in C++. And so you see the problem here, what they give you, candy per person. You would divide the number, let's say the items of candy in total by the total number of people. 9 divided by 4 is 2.25. However, you see when we divide two ints, the result is an integer. And the reason is C++ will only give you the precision equal to the precision of the most precise number used in the calculation. That's why candy per person equals 2 here, because we're dividing two ints. Right? So it kind of interprets the result as an integer, so anything in the mantissa, past the decimal point is truncated, and we are left with an integer. So that's why we have 2 and not 2.25 here. We can manually cast this, and we'll see an example here. All right, so first of all, we already saw that if I divide two integers, I'm going to be left with an integer. So 2.25 converted to an int, basically the mantissa is truncated, so 2. Now, like I said, C++ will interpret the result as the precision, the result will equal the precision of the most precise, operand in the calculation. So 9 divided by 4 in this case is going to give us 2.25. Let's see. Yeah, so what it did is it promoted, this is called promotion, it promoted the result to a double. And that's why we have the fractional portion there. Now what we also can do, let's say, all right, int double equals 9, so now 9 divided by 4 is going to equal 2 again, but, here, we'll call them, we'll not confuse things, we'll call them my int 1, my int 2. So now, what I'll do is I'll perform a little trick here. I will cast my int 1 as double. So that way we'll have a double divided by an int. Therefore, C++, the compiler, should promote the result to a double. So I would expect 2.25 again. Let's compile and run. 2.25. So this is promotion. Now, the way I've been casting, the way I've been promoting these here, I've been casting using kind of a deprecated cast, if you will. So you see the new cast here, static underscore cast. Then you have your templated parameter there, which is, or your templated type, which is double. In this case, we're putting double in there, which means we're casting to a double. Although I could put any type there. The compiler won't necessarily let me do that, but I can put any type in there. So this will perform, this is the new safe way of performing a cast of, let's say this variable total candy to a double. So let's see here. See if this works. Yes, same thing. Okay, this is just the newer, safer way of doing this. When I learned, we were still using the old, the old style. But it's, like I said, it's deprecated, so it may not be included. It may not work in future versions of C++. Use the static cast. Okay. So here's a good point. Order of operations. Watch this. What's going to happen if I do this? What do you think? Any guesses? Okay, well, look at what we're doing. We're casting this result of this integer division to a double. So let's see. Ruh-roh, Raggy. So here's what happened. We divided an int by an int, and we got an int as a result. Then we casted the resulting int, which is 2, to a double. Okay, fine. The result is now 2.000000, but that still leaves us at 2. So remember, order of ops. Okay, that's why that will not work. Notice it doesn't matter. I can cast the first type to double or the second type to double. As long as double is going to be the precision, double is the precision of one of the operands. You saw I was doing the old cast, where it doesn't mean I'm old. I'm not that old, but this is how I learned it. So yes, it's deprecated. Notice it says it may be discontinued in future versions of C++. That means it is deprecated. Don't use it. Try to avoid it. So we got some questions here. We know what this is. Okay. What's this? Row. So it performs the integer division and then assigns a result to a double. So it's going to assign an int to a double. So sure, now the result is 5.00000. However, it's still not, it's precise but not accurate. Okay. These I leave as an exercise to you. Easy enough. You should know these. We can look right at these and figure out what they do. Convert the following to C++. Well, here's a square root function, right? Here's, that's a quadratic formula. Here's a square root function here as well as a power function, and then just straight up arithmetic beyond that. And then we have here a power function, but keep in mind one of your arguments has to be an expression. That's all. You can do those easily. Programmer-defined functions. All right, so these are not the, the library functions. These are the functions that we code. Function declaration. Okay, this is the function prototype. So we declare, generally speaking, we declare a function and we define it. As you see, all I've been doing is defining the functions because the definition includes an implicit or explicit, really, if you want to look at it that way, declaration. So the compiler doesn't gripe at me because it has the method, the kind of the function signature, the function header, I believe they call it in this book. So you see, let me go back to an example here. Yeah, so here's an example of some code that I wrote here. You see, I only define them. I don't declare them. I don't just have the declaration. I have the declaration and definition. The compiler accepts that. Okay. So this is what a declaration looks like. Basically, your return type and your function name followed by the parameter list. So if I were to create a declaration for this fill method, it would look like this. That's it. That is a function declaration. And this really helps us when we want to build libraries. This can be included in a header file, and this will help us locate function. And then definition is what I've been doing, right? We have basically our header here, and then we have the body of the method also. So it kind of combines everything into one. If I'm not going to be coding libraries, I just do a definition. I don't declare these. Okay, we saw this. It includes, first the return type, then the name, and then within the parentheses, the number and the types of the arguments. Now, here's a little gotcha. Here's a little pitfall. A lot of people kind of mess up on this one. You see the formal parameter names. If I come up here, let me go back to my program. It looks a little complicated, but it's not at all. So you see I call my vector V here. Don't worry about what a vector is. Don't worry about any of this stuff. Just know that my parameter here is called a V, right, in the fill method. If I come down here, I'll call this V underscore underscore. It should still compile. Fingers crossed. Let's see, V was not declared in the scope. Where am I? On line 30. Oh, okay. Yeah. So I would have to change. You see all of my calls to find. Actually, you know what? This will be easier. I'm doing things the brute force way. We'll make this a whole lot easier. I'll keep everything the same. In my fill. There we go. Notice I'm calling fill with an argument of V. However, when I come up to fill here, in my parameter list, I have V underscore underscore. That is not a problem. Don't worry about that. It's not a problem for the compiler. Okay? It doesn't know what you are passing it in advance. As long as it is passed a vector of integers, and don't worry about what that is yet, it's happy. Doesn't matter what you call it. Okay, so these two don't have to be called the same thing. The compiler just knows what it's looking for. It doesn't care what it's called. When it catches, when it receives the value, when it's called, it will substitute the value in here for V underscore underscore value V. Okay, so that's that. The definition, of course, the definition kind of includes a header and the method, the function body, which actually does the work. Okay, they call this the function header. You can also see this referred to as the signature or the method signature. A method and a function are pretty much the same thing. And basically that just consists of the return type, the name, and then the argument list. Return type. Notice I said return type just a minute ago. This returns a double value, a double floating point, double precision floating point value. Okay, that means it'll give it back to whoever called it. It will substitute in for any expression where it is called. Okay, a return value doesn't have to be a literal or a single variable. It can be an expression. You see, for example, instead of returning a literal or a single variable, we have return subtotal plus the subtotal times the tax rate. So what this does, apparently this belongs to a function which calculates the total with tax for an item. So that's a valid expression for a return type. Okay, and we saw the call, we saw square root 90, right? The name in the argument list. Here you go. So a bill, so really all this will do, this will return the number times the price of the items. So this is a pretty simple, totaling routine for, let's say, some sales application. Okay, so we're calling a function named total cost that takes, an integer argument and a double precision floating point price argument. It multiplies those two inside the function. We don't see the definition, or we don't see the declaration or the definition. However, what they'll do is they'll multiply number times price and return that. Okay. We will get into call by value versus call by reference in later chapters. However, just know that the values are plugged into the parameters at the function end when it's called. They are plugged into, we go back here, we saw that the value of the vector v would be plugged into this v underscore. Okay, that's not the case here because this is a call by reference parameter, but if I were to do this, it would be accepting a plain Jane vector, and it would push the value of the other vector into, v into v underscore. And that's every time I call it. Okay, we have two forms for declarations. So for declarations, remember this is declaring and not defining. Declarations, we can choose to include the variable name if we want. You saw I did that earlier. If I control Z sum here, I'll see that. I thought I put there it is, yeah. So you see I did put a V there. Should compile. However, I can choose to also not put one there. So 6 of one, half dozen of the other. You can do it if you want, or if you don't want to. Okay, so the actual header itself in the definition does have to list the formal parameter names. How else, if I do this, I don't have a name for my, oops, sorry. If I do this, when I call this function, how am I going to refer to this vector? So that's why the headers have to include the, the variable name, the parameter name. Okay. Order of arguments. As I said, it doesn't compare names. So the compiler won't do this logic for you. So if you have a function, called grade that returns a character, it takes in two ints. All right, one int is received score. Okay, so I guess what this does is tells you fail or pass. Okay, so you input a score, and then you have your minimum score for maybe failing or passing or something. Now, if you flip-flop these arguments, if you accidentally pass it the min score first, and then the received score second, it will not know to flip these. Okay, the arguments are passed in the order of the function call. So this min score would be passed into received PAR in the function, and then received would be passed into min score PAR. Even if they're called the same, even if the variables are called the same, the compiler doesn't care. It will push the first argument into the first here, and then the second into the second. So be careful with with logic errors this way. The types match up and are correct, you will receive a logic error, but not any kind of compiler error. Within a function definition, first you'll usually have your variable declaration. You can come in here with this You see what I did here in this find definition? First I declare my arguments. Okay, usually you'll see them declared at the top. You have to, of course, declare, I said declare arguments, I'm sorry, declare variables. You, of course, have to first declare your variables before you can use them. Yes, typically declared before the executable statements begin. We saw that I declared my, my local variables inside the function at the top. Okay. At least one return statement must end the function. This isn't really true. You can omit the return statement and it will return void. And you can have multiple return statements in a function. Just be careful, okay? You don't want to litter a function with return statements or the flow of control is a little bit broken and it's hard to follow. But just know that you can return, you can have multiple return statements in a function. The first return that is found is the definitive value that is passed back to the caller. So once you hit a return, that's it. The function will return that value and the function will stop executing there. Okay. All right, so yeah, as I said, you can choose to declare or you can just go ahead and define it. That's what I prefer to do. Okay. Yeah, as I said, when you have the declaration, this will help you build libraries. We aren't worried about libraries yet, but you do need to know what a declaration is. Okay. We can return true or false Boolean values. Okay. And you see what they're doing here. So this is a little bit silly to look at. If the rate is between 10 and 20 or the rate equals 0, well, we could just say if the rate is appropriate instead. We're kind of outsourcing, if you want to think of it that way, this calculation to the function called appropriate. And if we need to make changes to this, we can make changes only in this function appropriate. Especially if we use this calculation at more than one place in our program, it's going to be a nightmare if we have to change it in the future. If our appropriate rate changes, to hunt all occurrences of this expression down in the program and change them. If we have it in one function, we can do it once in one place, and that's it. So yeah, you see, all we did was outsource calculation to appropriate. That way we have it in one handy place. We don't have to change it multiple times. It clutters our program less, right? And maybe it's a little bit more cohesive, if you will. And you can do these. Call by value. That just means that the value of the argument passed is plugged into the parameter in the function when it's called. You should be able to do this one. It takes 3 arguments. You just add the 3, right? Return them as an integer. Okay. And for one int and one double, you'll return an average of the 2. So really, all you would do is add the 2 and divide by 2, right? Because if you add a double and an int, that's going to cast to a double. It's going to promote the data type to a double, and then you divide by 2. Dividing a double by 2 will give you a double, right? Because you already have a double precision in your calculation. All right, procedural abstraction. So it sounds kind of fancy-dancy, but it's not. All this is saying, we have the black box analogy, and a black box is something that we can't see into. We don't need to be able to see into it, right? We put something in the black box and we get something out of the black box. So really how that relates to us is our functions, we pass them values in and we get values back. Someone who uses our functions in the future doesn't need to worry about the implementation. We're kind of separating the interface from the implementation here. So as long as you provide the function with the correct values, you'll get the correct values back. That's all any end user need to know about it. Okay? So when we write functions like this, we're kind of abstracting these details away from our main program or other programmers that may call these functions. Let's say for web services or something if we're using a web interface. Now, one of the advantages is information hiding. This is good for security. It's good for not being able to change variables that may otherwise be exposed. It's good for helping people not to shoot themselves in the foot by giving them too much information and stuff to manipulate. So designing with black box, we can change this in the future. If we have a simple interface, we're getting values in, returning values, we can, let's say we find a bug in our function. We can change that easily and keep the same return, let's say input and return values, and we don't have to, we don't have to put any burden on the other programmers. They can continue to use our interface as is with, with future iterations. So really, that's just coding your functions as if they, like black boxes. Okay. So, as I said, you're abstracting the details away from, the actual code. Okay. And yeah, good practice. Comment. If you have, if you're using web services, WSDL will help a little bit. You can comment these. You can have usually you'll have, the definitions in, let's say, a user manual, how to use them, web services guide, something like that. So yeah, conditions required of arguments, and you should describe what comes back as well as what goes into it. That much should be into it. Okay, functions are self-contained. This is kind of, okay, that's kind of a captain obvious. Everybody can contribute to different functions inside the same module. Yeah, so for formal parameters, you don't want to obscure things too much. You want your code to be self-documenting to the extent possible. As I said, formal parameters may or may not match the variable names used in the main part of the program. You don't have to match the variable names when you call a function. The compiler will substitute those values into the new variables. So we have a little case study here of buying pizza. So, what we're doing is a minimization problem, our cost per square inch. If we were allowed any size, then this would probably be a calculus problem. We'd get the first derivative and set it to 0 to look for a critical point in the minimization problem. However, it's not. We're given discrete sizes of pizza here, and so we're trying to figure out which is the better buy. And we won't spend too much time on this because our goal isn't to cover case studies here, but of course, the quantity is going to be, the quantity is based on the area, and the area, the formula for the area of a circle is pi r squared, okay? Pizza sizes are given in diameter. Diameter is twice the radius, so what, half diameter squared, times pi. So our function takes inputs, 4 inputs, actually it looks like. So the diameter of pizza 1, the cost of pizza 1, diameter pizza 2, and the cost of pizza 2. And what it will do is look for the cost per square area of the pizza and return the one that's better buy. All right, so get the input data. Then, we notice we've broken this task down into subtasks. And we could do this all in one function. It might not be ideal, though. We want code to be, maintenance is very underrated, so we definitely want to have a logical, cohesive program here. So subtask, get input data for each size of pizza. Okay, so we'll get the sizes. Then we'll figure out the price per square inch for each of these. Then we'll say, hey, this one's a better buy, and we'll output it to the user. Okay. So if you look, subtask 2 and subtask 3 are very closely related. So we can really do this with the same function. This one function, price per inch, will cover the smaller and the larger pizza, so we can group these together as a single function. They return a single value, of course, price per square inch. Okay. So we're calling this thing unit price, since our unit is a square inch. So this is what it might look like. We're returning a double. It's a function called unit price. We're taking the diameter of the pizza and that's a little typo there, and a double price. Makes sense, right? Price per square inch, price divided by diameter. Well, actually, the formula based on the diameter, the area. All right, so we're back to 1 and 4. We've kind of figured out how we want to do 2 and 3 in the same function. 1 is get the input values. Yeah, of course, we'll need to push them into variables if we're going to pass variables. Okay, they're calling them diameter small, diameter large, price small, price large for the for the diameters and the prices on the pizzas. Okay, so we're left with 4 and 5 also. Compare the cost per square inch. Okay, so we're going to figure out which is less, and then we're going to display that to the user. All right, 2 and 3, we already have our unit price function in mind. Right, we'll compute the radius, and actually that's going to be another typo. The area, which is going to be pi r squared, or pi times 0.5d squared. And then we will return, our price per square inch, because that's going to be, the area square inch is going to be the result, the output of this calculation. So pseudocode is a kind of a mix. It's not quite pure English. You see some examples here. Now, we don't want to completely describe what we're going to do in English, because anybody can do that. We don't want to necessarily start coding just for the sake of starting coding and only writing C++. So we can put comments in here that will tell us, hey, radius is half the diameter. Area is going to be pi times radius times radius, because we haven't formally defined pi yet as a constant. And we know what we want to return. So we can kind of write this stuff out. When we're planning for especially large programs, pseudocode is going to be important to us. Okay, we want to know what variables we have, what we're going to do with them, and this will kind of allow us to express a mix of English and programming. Okay, so what main can do is define the doubles, and go ahead and get the unit prices for them. Unit price, here's the definition of unit price. So we have a constant, that it's pi out to 5 places, and we are calculating area, and then we're returning the price per area. But there's a bug here. Radius should include the fractional part. Let's see, why doesn't it include the fractional part? Oh, you see the problem. Diameter is an int. An int divided by an int is an int. So our radius will be a little bit off. If let's say we had a 10-inch pizza, that's fine, because 10 divided by 2 is 5. However, let's say our pizza came in a 13-inch size. So at a 6.5, this would be calculated at 6. So we'd have a little bug in our program that wouldn't always be visible, right? I imagine that pizza sizes, at least the ones I've seen, are usually expressed in even integers, like 8, 10, 12. You want to go family size like 16, 18, 20. But if we ever have non-even sizes, we'll have a problem. And so we're casting a double. Okay, so that's one possible solution to it. We can cast either one of these to double. Or, we can accept diameter as a double. It'll promote upon passing the argument to the function, however you want to do it, as long as you see the problem there. So we can have logic errors. We have syntax errors, which the compiler will many times catch, or at least warn us. And then we have logic errors, which the compiler will not catch. Just because your program compiles and runs does not mean it's correct. Okay, so what we'll need to do, testing is a whole nother, there's a whole their entire graduate classes, software engineering classes on testing. But what we can do, we can run some test cases through our program, and if we compare them to what we know to be correct and get the right answer for each of those, it kind of increases our confidence that our program's correct, or at least correct to a certain extent. As I said, in programs of any appreciable size, bug-free is impossible, but we can at least minimize this and have some more confidence. Okay. And several sets of data is good. We'll want boundary cases. So yeah, you can't rely on one result, is all this is telling you. You have to test with different inputs, and you want to look at boundary cases and such. Yeah, see, and here's what I pointed out. You won't always get the problem here. So if you only input 6, 8, 10, 12, whatever you know to be normal pizza sizes, you won't catch this bug. Only if you put odd numbers in will you catch this little bug that we saw. Okay, and pseudocode, you don't use pseudocode just to use it. So, as it says here, if the step is obvious, just go ahead and code it. Now, if it takes some calculations and complicated shuffling, whatever, then you may want to go ahead and use English or mix, pseudocode in the function. Well, as you're planning it. Purpose of a comment that accompanies a function declaration. Well, it's up here, right? And the return value. What it means to say a programmer should be able to treat a function as a black box. You put values in, you get values out of it. You don't care what's inside of it. That's, you kind of abstract those details away from, a programmer who's using your function. If two functions are black box equivalent, all that means, and I didn't see this in the slides here, but really all that means is that your input and your output's the same. If you want to think of it in more concrete terms, the return type is going to be the same, and your function header is going to be the same. Okay, so if two functions are black box equivalent, they do the same thing. They may not do them in the same way. All right, local variables versus global variables. The variables defined in a function live inside that function. Okay, we have this concept of scope here, and scope is where a variable lives. If you declare a variable in a function, we'll go back to my program here with vectors. All right, inside this find function, I've declared a double called total position. Notice it's within the brace identifiers that delimit the function. So as soon as I hit this closing brace, this matching end delimiter, double's gone. Double's out of existence. This particular double here. So if I come in main and try to reference total position, well, main's out of scope because my total position variable lives from here to here. So if I try to do this, and if I try to reference total position in main, I'm getting it's not even going to compile. Yeah. Okay. Yep, total position was not declared in this scope. It says, I don't know what this is. It might have been declared elsewhere. Okay. Okay, so variables declared in main are local to main. Okay, so check this out. Sorry, just one second. All right, sorry about that. So, we're not only limited, when we talk about scope, we're not only limited to talking about, function bodies. And we've seen this before. We'll just kind of have an empty loop there. What do we think is going to happen now? So you have my int I there. My loop starts here, ends here. What do you think is going to happen? Yeah, of course. I was not declared in the scope. So, we're not only limited to talking about, blocks. We could have nested blocks. We can have blocks within blocks, blocks within functions. When I say block, I mean something that starts with a curly brace and closes with a curly brace. Globals. Okay, so we can have global constants. We'll take a look at we'll actually create a program here. A constant is declared outside of any function. Usually at the top. Well, here. We were just talking about, I guess, area, so this is a good example here. I'm not one of those pocket protector guys who spy out to 100 places, sorry. My apologies to you if you wear a pocket protector. So we'll say the area so what do we have? We have pi r squared. So 2 to the, oh, no. This is going to be 5 to the 2, right? And that's pi times 5 squared. Okay, so 5 squared is 25 times 3 point something. So we're going to have about what? 77, 78. Let's see here. Oh, I didn't include my math. Better. So this is an example of a constant. Again, constants are declared outside of any other function. The convention is to do them at top. The convention is to do them in all caps. There we go, 78.5397. So the advantage of constants really, if we have something that can change, especially something that can change, well, it doesn't even have to change. So let's say, I know this from memory, 3.14159, blah, blah, blah. What if I wrote it down wrong? What if we include it in 20 different places in the program and I wrote it wrong? Or let's say we have our current interest rate is 5.5. It could change tomorrow depending on what the feds do. Could be 5, could be 6. This way, I don't have to hunt this constant named interest rate down inside the program in 20 different places. I change it once here. Oh, sorry, we changed to 5, and it's done. So this is the good thing about constants. Okay, and constants and any other variable that we want to declare to be global we'll put outside of any function. Caution using globals. Don't really use globals. Don't use globals unless you really know what you're doing. They have the capability to, of course, they can be modified anywhere within the source file, within the source program, and it can be a nightmare tracking down the changes to them. So try not to use globals unless you absolutely have to. Constants such as this are fine. Yeah, so that's a good point, and I didn't say this explicitly. It should have been obvious, but I guess I'll go ahead and say it. So pi is going to be available to any function, including main, any function that I will define inside this source file, okay? A global will be available to any function inside this source file. Yeah, you see, generally makes program more difficult to understand and maintain. This is because global variables can be modified from anywhere inside the program, and this is kind of a software engineering maintenance nightmare. Formal parameters are local variables. You notice if I come back to my vector example here, V is only accessible inside this scope. Just like I is only accessible inside this loop. Okay? You cannot redeclare them inside the function body. I believe the compiler will give you an error. If I'm not mistaken, I'll declare an int called DE. I believe it will warn me about hiding this variable. At the very least, it should warn me. Sorry, just a minute. Let me do this. This may be clearer to us. Can't spell today. Yes, shadows a parameter saying, oh, you hid your function, you hid your parameter there. So not good. Now if I take it out, it won't warn me about that anymore. It looks like I may have other problems here, but you know, this is the one we were looking. Shadows a parameter. Block scope, as I said, blocks are inside, you know, everything basically inside the you know, curly brace delimiters, that's a block. And you can't have nested blocks. Now notice I have the start of a block here. I also have the start of another block. And heck, even the start of another block. But notice that inside this block, nested inside this block here, nested inside this block here, I can still reference my vector. That's because vector, you know, my VE vector lives anywhere between here and here. And that includes inside this nested block. All right, factorial. So there's just kind of an example of the factorial function. And that would, you can use a while or you can use a for to code factorial. You can do this recursively, which we haven't really learned about recursion yet. But an easy way to do it would be you can define a function. We know it takes an int. We know it returns an int. So you know, really factorial, what factorial says is that 6, factorial 6 would equal 6 times 5 times 4 times 3 times 2 times 1. So factorial is the number times every number less than it down to 0 or down to 1. So you know, we could say we'd have a total to keep count of everything. We could increment up, we could increment down, whichever is more kind of straightforward to us. That probably should work. So this can be a simple factorial function. And you can do this however is kind of most intuitive to you. Let's see, global. Oh, you know, I did I've got databases on the brain. I did an incorrect comment style. That's what it was griping about. Oh, I didn't have a closing parentheses there. Looks like I've got an infinite loop, and you see what I did wrong. There we go. I didn't decrement because I started at the top, working my way down to 0, and I incremented instead of decremented. So I never hit 0. That's why I kind of did a runaway loop there. So 6 factorial equals 720. I'm not sure if that's right. Let's see, 6 times 5 times 4 times 3 times 2. Oh, look at that. All right. Got it right. Just got some compiler errors, but my logic was correct. Save that. That was a silly logic error. Overloaded functions. So remember, functions have a header or signature, whatever you want to call it. The book calls it header, so we'll stick with that. So we can change these headers and still maintain the same function name. Remember, a header is a return type followed by it's basically the function name with the parameter list. So if our parameter list is different, our header is different. Sorry, just one second. All right, and so when our argument list changes, that basically changes the definition of the function. So it becomes a different function for all intents and purposes. So here we have two different, basically examples of two different functions. They're both called AVE. They both perform an average on different, varying quantities of numbers. Okay, so we have one for 2 numbers and we have one for 3 numbers. You see the difference in the parameter list here. You see the difference in how they're calculated. Average is the sum divided by the number of items that we're summing. So what the compiler will do here, if you call average with 3 parameters, it knows, it looks for a matching header or a matching signature, and it will insert 10 into N1, 20 into N2, 30 into N3. If I were to just call it with 10 and 20, then we would just use N1 and N2. So we can see, we'll do a real quick example here. We'll have one called cout. I don't want to waste time with calculations. We'll have one that takes 3 integers. All right, and I'll copy this to save time. I don't want to waste your time. I don't want to waste mine. All right, and we will indicate that we're in the one with 2 arguments. Okay. And we'll just go ahead and call these 2. So here I'll call the second one defined rather first. And then here, this should call the second one, right? Because the compiler will look at this first call and say, okay, I have a cout with 2 arguments here. So it should call this one. Then it looks at this and says, okay, I have a cout function with 3 arguments right here. So I'll go ahead and this one. So let's let her rip. Wait until it stops compiling. Oh no. What did I do? I3 is not, oh, there we go. Okay. Yep. So there we go. That's it. So the compiler will do this for you. If you overload the methods, the compiler will look for the matching signature or the matching header. So yes, they have a different number of parameters. If you define it twice, problem. Watch this. Now we have 2 of the same function. That doesn't jive. Compiler will not like that. Good. Okay, you have to have at least 1 different type of parameter. Okay, so yeah, that's a good point. We could do this. I have the same number of arguments, yet a different type. Let's see what we get here if I do this. This will be interesting. Let's see. Oh, yeah. All right, good. So you see the first one, it recognized that we had two ints, so it called this function. Here, the compiler says I got an int and a double. It says I'll cast if I have to, but first I'll look for exact matching arguments. And I have one here. I have an int and a double, so it called second function second. You know, I could have said, you know, with double or something like that, and that would have been clear point. All right, so here we have an example of the pizza program. Instead, it's rectangular pizzas. You know, really all we're doing is changing. All we're doing is changing the implementation, kind of the calculation here. That's it. Calculation of the price per square unit or unit. The unit's still going to be square inch. However, the calculation is now different because length times width is how you calculate the area square rectangle. Yeah, as I said, the compiler, if it doesn't find any matching, any exact matching function headers, it will cast, it will promote if necessary. It won't depromote, but it will auto-promote. So it'll convert ints into doubles if nothing else matches. Okay, so in this case, the value of the arguments are converted to type double. And really, what all they're saying is, you know, keep in mind, just pay attention to what you're doing. Because if you look at this, you know, if we redefine this as an integer, all right, so what we want to do, we want to measure the, number of perfect goals. So we have MBG measure perfect goals. We're taking two ints in. We're returning goals minus misses. Rutro, you see what we did? You see the problem? Kind of shut ourselves in the gear. Okay, because, like I said, the cloud is going to look for matching types, exact matching types first. Well, it's not going to have to promote. It says, hey, I already have two ints. I'm going to use this measure perfect goals function because it matches, the header matches perfectly. Just be careful. Okay, don't use the same function name, different functions. All right, so top-down design, when we break tasks iteratively into smaller subtasks, and then the units are small enough to easily code, trivially code. Okay, types of tasks we've seen so far that could be implemented as functions. I'm not going to go over this. Black box, you put stuff in, you get stuff out. You don't care what's in the void, in the black box there inside the function. Procedural abstraction, abstracting details away from the abstracting implementation away from the interface, what you actually see. Information hiding, not giving everybody access to all the inner workings and not being able to screw things up, shoot themselves in the foot, etc. Finding a local variable, that's a variable inside a function, right? That has a limited scope anyway, it's not global, let me put it that way. Overload a function name. So remember when we change our header, when we change the arguments, either the number of arguments or the type or both, then we are function. Okay, so I guess that's it here for chapter 4, and I'll see you in the next lecture.